because the design is done at a particular node, at a particular process, because the transistors, they are like each foundry will have a different transistor. Even if it's a 1.8 volt transistors, the models of that transistor, by model I mean IV characteristics of that transistor, VT and all that, that will vary from one fab to another fab. And so that the electrical characteristics, electrical properties of the various gates will vary. Their delays and parasitics will vary from one fab to another fab, from one node to another node. That is why it is specific to a foundry and specific to a technology node. So all these foundries, they will give you their standard cell libraries having more than 600, 700 different types of cell. They will have so you have to use those cell libraries, and timing constraint the designer has to give. Like if your design has to work at some 1 gigahertz kind of a clock rate, that constraint the designer has to put in a software code. It will choose, while doing the synthesis, it will choose those kind of cells so that those timings are met, and what kind of clock are coming from the input, and all those things have to be given. And once you have done the synthesis, and finally it shows in terms of various gates and flip-flops, and then you will decide the floor planning, which is a very important part. How, like in a house, where you do the bedroom, where you do the kitchen and things like that. So there are certain guidelines for doing that. Like if there is a signal which is a very rapidly changing, very high speed signal, so that circuitry has to be properly guarded, and it should be away from any low noise analog signal. So that because the substrate is same, so that the noise is not coupled to the analog. The frequent high speed change of any digital input can be coupled to the analog, and thereby creating some noise there. So some guidelines are there in the floor planning where to, because in a uh, complex design, there are various blocks, and those blocks cannot be randomly placed. So they have to be placed, and there has to be some nets connecting between those blocks. So the overall, you can say the length of those nets have to be minimized, because those lengths will decide two things: the speed of the circuit and the power dissipation also. So power dissipation also is there in the nets. So shorter the length, better it is. So that way you have to decide on the floor planning and placement. Then the tree, because now a synchronous design, there is a single clock which is coming. Either it's being generated inside the chip by PLL or DLL, because if the circuit is supposed to work at say 400 megahertz at 130 nanometer or 180 nanometer, it's very difficult um, to give a clock through the pads, because pads have those big diodes for latch up protection and ESD protection, particularly ESD protection. So they will not allow a 400 or 500 to go inside from the outside. So from the outside, there is a very low frequency clock, say 10 megahertz or 100 megahertz kind of thing. And using PLL, you can generate very high frequencies, 500 or 1000 megahertz, 1 gigahertz clocks. And those clocks have to be given. But each clock, if the length of if the dimension of the chip is 10 mm by 10 mm, so that clock has to go at all these corners at the same time, otherwise there will be clock skew. So the how to do the synthesis, that clock tree synthesis, that also is important. And then finally the routing of these various nets, and after doing the formal verification and the timing analysis and simulations and things like that. So this is basically the design flow and the technology files which are used, because it's any design has to be made at a particular technology node. So you need the technology files, you need the physical library, how the layout, what are the different layers used in a cell. You need about the IO pads, normally are supplied by the foundry. You cannot design an IO pad because the process is involved in there, because there are big doubts. And so IO pads are normally like a standard cell library. The IO pads are also given along with the IO cells. Okay, so all these technology files and timing related information, then their model parameters, all that information is there in the foundry where on which we have designed the circuit. So this is how in a digital design ICC Synopsys is a very good flow. It's a very good tools for digital, and I think 70-80% of the time Synopsys tools are used. So IC compiler, commonly known as ICC, is the one which is the heart for physical backend design. So these are the four inputs which is needed. So it needs a synthesized level netlist, gate level, after synthesis, which has information, as you can see, it has information of various gates, how they are connected to each other. What are the inputs of the gate? What are the output? How the output of the gate goes to the input of the next gate. So that information, that is a netlist, which is a output of the front end. Then, as I told you, it needs technology files. And these are the technology file. It needs layers and parasitics, design rules, and unit definitions, what type of standard cell library, IO, power rated, and all those things that Foundry will give you. And timing constants you have to put, designer has to set. What kind of timing, what kind of frequencies you need for the clock and for the input. And this timing constants you have to give. And logical physical library are again a part of the technology file. So with all this information, the IC compiler will take the gate level netlist and generate a design which look like this. So here you can see there is some block here which is a processor. So it's an IP, it's a black box for you because you have not designed, you have taken it from some other company. It's a, say for example, 32-bit processor you have taken from other company. It's a black box for you. They have given you only the IO specs of that. Placement of this becomes an important thing because this IO, this processor will be interacting with various other elements, various other blocks. So where it's having frequent interaction with some memory or some any other IO, so you have to place in such a manner the overall functionality has been met. So that is a part of the floor plan. This is just to explain one example. There may be some 3-4 such blocks, and so the placement of those blocks are very important. So that's why the floor plan has to be done very carefully. Example of technology files like what are the layers, what are the names of the layer, what are the abbreviation, what are the number of the layer, what is the color. So that information is there in a PDK, process design kit. Okay, so then there is a information about the RLCs, basically the parasitics, and that unit information is given, like how much, what is the resistance per unit of the interconnects of the nets. And once you do the placement of these coarse placement of these blocks, and you do the routing, so you know the length of the nets, and you know the RLC per unit, so you can calculate the total RLC. So RC extraction, because inductor is important at below 90-45 nanometer, inductor is also important. So those things you can do, and then take into account to simulate the circuit using parasitic of the interconnects. Now the standard cell library, which is a logic library, what it has? It has a, what is the characteristics of the cell? It's a 2-input NAND, 3-input NAND, NOR, flip-flop, what it is, what are the various timing diagrams, how much power it takes. Okay, so what are the design rules in that, and what is the operating conditions? So all these things, and what is the fan out and capacitances, all that information for each cell is given in the PDK. Each cell, there may be like SCL library, there may be some, there are 500 40 plus cells, and such information of each cell and how these timings vary with temperature, high temperature, low temperature, how they vary. So those things, those details are also given. So physical library is just a layout. Like this is an example of one cell which is an inverter. This is a cell view which is an inverter. It has all layers. As you can see, different colors are there. It has all layers. But the phantom view, this is known as a phantom view. When you are interconnecting the blocks, you need only the points where you are doing the interconnects, where you are connecting. So you will be connecting at the input here or at the output or at the VDD or VSS. You need this only. You don't need the other layers, like which may be a well, which may be a diffusion, which is the active layer. So those layers you don't need when you are interconnecting. Okay, so that phantom view is used. That is known as an abstract view only. It contains minimal data because nowadays, as you see, the number of cells are very high, millions. Each cell has lot of data, and if you take all that data and you are trying to do some simulation or something, it becomes slower. Okay, so where you don't need all these layers, you can only see the interconnects. So this is a very simple cell. Similarly, for a macro cell and for an IO pad, all this information will be available. Phantom views are available in the PDKs. Constraints is you have to do, you are the designer. What are the constraints? Because a chip fits in a circuit, in a board. So the chip is getting some clock which is coming from the external world, coming from another. So some of these inputs may be coming from another chip. So there is a constant with how much delay they are coming and what are the voltages, input VIL, VOH of those, because they are coming from somewhere else. It's not an isolated chip. It's going in a system. And similarly, output is being fed to some other chip. So there will be constraints on the input side as well as the output side. And the constraints of clock will be in terms of the frequency, which is a period, and what is the duty cycle, and how much skew, like how much clock edge placement accuracy, EPC, how much clock edge can vary, how much it can change. That will, how much skew can be there is tolerable in your design. And similarly, delay can be how much delay at the input and how much delay at the output. All those things, those are they form the design constraints. And based on this, finally the physical layout has to satisfy all these things. So this is how these things are done. Now the first point, the first design activity in a physical part is a floor plan, because in a circuit now there are many IPs, there is a lot of memory, and memory is not in one chunk. They are different instances of memories. Like memories, they will come in different instances. There may be some 40, 50 or 100 instances, because you will like to place the memory as close where it is needed. It's a cache memory. You will like to put it very close to the arithmetic logic unit. So as the example here, there's an IP, there is a RAM, there is a ROM. So where to put IP, where to put ROM, how to make these, you can say the IOs. These are the IO pads. So how to distribute these pads. So all these things is a part of the floor plan. And number of IOs are also more nowadays, more than 1000, 2000 IOs. And overall goal is obvious. These three, you have to minimize chip area. You have to minimize dead space. Like these are the dead space. You have to minimize. You have to make, because all these blocks, they will interact with each other. You have to make the path of these net minimum. And routing should be easy. So it should be done in minimum metal layers. More metal layers will you can degrade the performance. So if you are able to do in very minimum of metal layers, minimum length of nets, and minimum dead space, that design is supposed to be the best and it will meet all these specs. It will have less power and more speed. Okay, so the floor plan